So in this video, we'll be discussing about the input and output organization. As we know that processor is the most important component of the computer system. Besides the processor, the next important component is the memory, where the data are being stored, data and instruction are being stored before processing. Besides this processor and memory, there is an important component. It's called the input output. Because we give input or we get the output for the system through some devices. So how this input output organization being carried out? So how to access these devices, accessing these IO devices, because there are some IO devices, each IO devices may be identified with some unique ID and they might be taking some memory space. How these devices will be accessed? So look into this diagram. We have a bus to which different devices are connected. IO device 1, 2, 3 up to n number of devices are connected. Besides that, to this bus, processor and memory are also being connected. So these, what are these IO devices? Maybe keyboard, video, hard disk, mouse. These are the IO devices which are being connected to this bus. So multiple IO devices may be connected to the processor and the memory via a bus. So bus consists of 3 sets of lines to carry address, data and control signals. The single line that you see over here, actually there are 3 lines over here, one address line, data and control. So 3 lines consist of this bus. So we have address bus, data bus and control bus. So each IO device is assigned with an unique address. So every device has a unique address. To access an IO device, the processor places the address on the address line. Suppose the bus wants to access the keyboard has a unique address. So bus will place that address in the address line and which can be identified by this keyboard. The device recognizes this address which is there on the bus and responds to the control signal. So for access, how this IO devices are being accessed. IO devices and the memory may share the same address space. It might happen that processor, or the IO devices and the memory may share the same address space. If that happens, we say it is a memory mapped IO. So no special instructions are required over here. To access any of the instruction the way we access, similarly we can also access the IO devices. These are called memory mapped IO. Any machine instruction that can access memory can be used to transfer data to or from the IO devices. The way we write the instruction to access the memory, similarly we can write the similar kind of instruction to transfer data to or from the IO devices. So it's a simpler software. However, the IO device and the memory may have different address space. This is called IO mapped IO. The first one is called the memory mapped IO, whereas the second one is called the IO mapped IO. So in IO mapped IO, what you have? The special instruction to transfer data to and from IO devices. So try to understand over here. Here in the memory mapped IO, we don't have any special instruction to access the IO device. The way we access the memory or accessing any other instructions, similarly we access for the data transfer. However, in IO mapped IO, we need special instructions for accessing the IO devices. So IO devices might have to deal with fewer address lines because there are few number of IO devices. So therefore, suppose I have 8 IO devices in total, so I might be requiring only 3 bits. 2 to the power 3 equals to 8. If I have 16 IO devices, I might be requiring only 4 bits. So IO address lines need not be physically separate from memory address lines. So the same address line may be used. But however, the instructions are different. In fact, address lines may be shared between IO devices and memory with a control signal to indicate whether it is a memory address or IO address. So how to differentiate? It will differ through this control signals. So see over here, this is the bus. As I said, the bus is actually, there are three lines over here: address line, data line, and control line. Suppose this is the input device, is a keyboard. The keyboard is connected to this bus. So this input device or output device, any IO device, is connected through this bus through a intermediary circuit over here. This is called IO interface. This IO interface has three components: address decoder, control circuits, data and status registers. The address decoder you can see over here, it is connected from the address line. Control circuits are connected to these control lines. Data and status registers are connected to the data lines. This is bidirectional, so we can send data and receive. Here the bus will only send the address to identify which of the device, which of the IO device. Control circuit will give the control signals for read, write, for different operations. So IO device is connected to the bus using an IO interface circuit, which has address decoder, control circuit, data and status registers. So address decoder, the address decoder decodes the address, places the address line through enabling the device to recognize its address. So what the address decoder will do, the address which is sent by the processor is decoded so that it will check that whether the address is for this input device or for this device or not. What the data register, status register will do, the data register holds the data being transferred to and from the processor. I may want to send data or receive data, the data register. The status register holds information necessary for the operation of IO devices. For operation of these IO devices, some information, additional informations are required. Those are being carried out through the status register. Data and status register are connected to the data lines and have unique addresses. IO interface circuits coordinates the IO transfer. So it says that out of all the devices, processor is the fastest device usually in a system, in a computer. And usually the IO devices are very slow. And the keyboard is found to be the slowest device in the system. So there is a mismatch in speed while transferring of data. So this creates a need for mechanism to synchronize data transfer between them. And this data transfer can occur in three different modes. One is called program controlled IO. Second one is called interrupt driven IO. And the third one is called the direct memory access. In program control IO, the processor repeatedly monitors a status flag to achieve the necessary synchronization. Processor polls the IO device. So we'll be reading in detail, but these are the three different accessing modes. One is program control IO, second one is interrupt driven IO, and the third one is direct memory access. Coming to the first one, the program controlled IO. As the name suggests, a program controlled IO, the entire IO operation is controlled through a program which is being governed by the CPU, by the processor. So CPU monitors the entire IO operation. So at the time the IO operation is carried out, the CPU is busy throughout the time. It is being monitored by the CPU itself. And for this, it uses some status registers to check the status of these IO devices. So programmed IO is implicated to data transfer that are initiated by the CPU under driver software control to access registers or memory on a device. So it uses a driver software which is nothing but a program. So it is controlled by a program, and who initiates? The CPU initiates. With programmed IO, data are exchanged between the processor and IO module. So data exchange between these can be done through the CPU monitoring only. The processor executes a program that gives it direct control of the IO operation, including sensing device status, sensing read or write command, transferring data. So all these will be governed by this processor. When the processor issues a command to the IO module, it must wait until the IO operation is complete. So until the IO operation has not been completed, processor has to monitor all the operation. If the processor is faster than the IO module, this is the wasteful. for the processor time, because processor is a very fast device and the IO devices like keyboard are very slower devices. So therefore, the processor has to wait till the words are not being transferred. So with programmed IO, the IO module will perform the requested action and then set the appropriate bits in the IO status register. The IO module takes no further action to alert the processor. See here, for IO module, for example, for a keyboard, whether keyboard is ready to accept or not, we have a status register for the same. Similarly, while displaying on a video or monitor, we have a status register to check that whether it is ready to receive the information or not. So all these are being programmed and is being controlled by the CPU. So no further action. So IO module takes no further action to alert the processor that I have done my work. See this figure. In this diagram, it can be seen that the processor issues a read command to the IO module. Suppose it wants to initiate, it issues a read command to the IO module. So CPU issues a read command to the IO module. So now IO module reads status of it. So IO module checks its status. So if it is ready, if it is ready to come over here. If it is not ready, the CPU again continuously checking the status. So CPU is busy in checking the status of the device. This is called polling. So a bit is there, a bit is associated with it for every device, is called the status bit. So every time the processor is busy in checking the status bit. This is called polling. During this polling, the processor is not doing anything else. It is wasting of the time. This polling is nothing but the wasting of time. This is all called the spinning. Spinning or polling. The processor is not doing anything, it's just spinning over here. You can see this till it is not ready, it's just spinning. So polling or spinning is just a waste of CPU cycles. So if it is ready, it read the word from the IO or it will write word into the memory. Then if it is done, it will over. If it is not done, it will go for reading the next word. So this process will continue. We can see it throughout this process. The processor is always checking the status of this module. If it is ready, then also the CPU is busy in reading or writing. So throughout the process, the CPU is doing all the work, and this can be done through a program by checking the status. So it's called the program controlled IO. This IO transfer through this program controlled IO is not so effective because of what? Because of CPU engagement throughout the process and this polling or spinning. Processor always busy in checking the status of the IO device, IO module. So the next kind of data transfer is called the interrupt-driven IO. To discuss about the interrupt-driven IO, first we'll discuss about what are interrupts. In program control IO, the processor continuously monitors the status of the device. It doesn't perform any useful tasks. So it doesn't do anything useful tasks, it will continuously check the status of the devices. This is also known as busy waiting. This is also known as busy waiting. It is busy in waiting for to get the status of the device. So it is not so effective. Therefore, an alternate approach would be for the IO device to alert the processor when it becomes ready. So why not, when the IO device will become ready, now it will alert the processor that I'm ready now, ready for transfer. So processor doesn't have to continuously check the status of the devices. So it do so by sending a hardware signal. This hardware signal is called the interrupt, the processor. So at least one of the bus control line called the interrupt request line is dedicated for this purpose. So this signal will go through, maybe one dedicated line is there. This is called the interrupt request line. The processor can perform other useful tasks while it is waiting for the device to ready. The processor doesn't have to wait to check the status. See over here. This is a program. the line 1, line 2, line 3 is go on executing up to line I. Suppose here the interrupt occur. It is suppose a scanf statement. Scanf statement requires what? The data to be inputted from the keyboard. So IO device is required or keyboard is required over here. For every interrupt that occurs for IO device, for every interrupt has a particular code to be executed. This is called the interrupt service routine. So interrupt service routine is assigned for each of the interrupts. So whenever an interrupt occurs, it goes for executing a small code called the interrupt service routine. So it goes to the interrupt service routine, execute all those instructions and return back to the next instruction to the main program and continues up to n number of instructions. Processor is executing the instruction located at address I when the interrupt occurs. Here the interrupt occurs in the ith location. Routine executed and respond to an interrupt request is called the interrupt service routine. Routine executed in response to an interrupt. Whenever an interrupt occurs, a particular interrupt request, interrupt service routine will be executed for that interrupt only. When an interrupt occurs, the control must be transferred to this interrupt service routine, ISR. The control will transfer to this ISR, and when it is over, the control will return back to the next instruction. This will enable the return from interrupt instruction to resume execution, so it will start executing from I+1. This return address may be stored in some other register or in a stack. So if you look into this flowchart, we will see that the CPU issues a read command to the IO module and CPU will go for doing some other work. So CPU now it is not checking for the IO status. When the IO is ready, an interrupt will be given to this IO status, read status of the IO module. It gives an interrupt that is ready so that IO will inform the CPU that the device is ready. It checks the status. If it is ready, the read or write operation will be carried out. Read module, write module will be carried out, either read or write. If it is done, if it is not done, then it will go for reading the next one. If it is done, then the next instruction will be carried out. So finally, we have another mode of access, IO access is the direct memory access. It's the faster mode of accessing the IO devices. The DMA, direct memory access, is DMA. A special control unit may be provided to transfer a block of data directly between an IO device and the main memory without continuous intervention by the processor. So DMA is a module which can directly transfer the block of data, huge amount of data, without continuous intervention by the processor. Processor will not be busy over here. Control unit which performs this transfer is a part of the IO device interface circuits. So control unit which will perform this transfer is a part of what? By part of the IO device interface circuits. So in the interface circuits, what do we have? We have control, address, and the status, and we have data and status registers. Now we have this DMA is a part of this. This control unit is called as a DMA controller. So DMA controller performs functions that will be normally carried out by the processor. So what DMA will do? What the processor was doing for transferring of data, now DMA is doing the same thing. For each word, it provides the memory address and all the control secrets. To transfer a block of data, it increments the memory addresses and keeps track of the number of transfers. DMA controller can transfer a block of data from an external device to the processor without any intervention from the processor. This I have already said. However, the operation of the DMA controller must be under the control of a program executed by the processor. So DMA control operation of this DMA controller is what? Is under the control of a program executed by the processor. So DMA may work independently, but however, it may transfer the data independently. However, it is controlled by the program executed by the processor. So that is the processor initiate the DMA transfer. So processor will initiate the transfer, gives the control to the DMA for the huge data transfer. So what information the processor gives? Three informations are given to the DMA. The starting address, number of words in the block, and direction of transfer. Direction of transfer means either from IO to memory or memory to IO. So these three informations are given by the processor to the DMA. So processor says from which address you start transferring, start transfer from which address, how many words to be transferred, or how many blocks to be transferred, and how many words are there in the block, and whether you are to is from IO to memory or memory to IO. Once the DMA controller completes the DMA transfer, it informs the processor by raising an interrupt signal. So once it is over, DMA has done its work, it will raise an interrupt signal that my work is finished. So it will give it to the control to the processor. So you can see over here is a system bus to which processor and memory in one side. We have some IO devices. There are some disks for which has a DMA controller. We can network device which has a DMA controller. So DMA controller connects a high-speed network to the computer bus. Disk controller which control 2 disks also have a DMA capability. It provides 2 DMA channels. So even if there are 2 disks, but it can perform 2 independent DMA operations as if each disk has its own DMA controller. The register to store the memory address, word count, status, and control informations are duplicated for for both the disks. Processor and DMA controllers have to use the bus in an interwoven fashion to access the memory because both are accessing the bus. Processor and DMA both are requiring. So DMA devices are giving higher priority than the processor to access the bus. Among different DMA devices, high priority is given to high-speed peripherals such as disks or graphics display devices. So high-speed devices are given the higher priority. Processor originates most memory access cycles on the bus. So most memory access cycles are being originated by what? By the processor. So what DMA is doing? DMA is also using some of the memory access cycles. So we say DMA is stealing some of the memory clock cycle from the processor. So this is called cycle stealing. DMA controller can be said to steal memory cycles from the bus, and this interweaving technique is called as cycle stealing. An alternate approach is to provide the DMA controller an exclusive capability to initiate transfer on the bus, and hence exclusive access to the main memory. So we may give a exclusive access to the main memory to the DMA. So only DMA can access it. Then that means the transfer speed will also enhance. And this is known as the block mode or burst mode. This is known as block mode or burst mode. So cycle stealing is what? Cycle stealing is stealing the DMA controller can said to be steal memory clock cycles from the bus. This is called the cycle stealing. And burst mode is for the huge data transfer. The DMA is given the exclusive access to the main memory. Hope you have understood.